This is the last topic about pointers. Pointers and allocation. When you declare a pointer, for example, an integer pointer PTR, it doesn't actually point to anything yet. It will point to somewhere that we don't know in memory, and it will contain garbage. So dereferencing it will usually cause an error. There are basically two ways to kind of resolve this situation. The first one is let it point to something that already exists. For example, we declare integer pointer PTR and an integer variable var. Then we assign 5 to var. This means var will have a space implicitly allocated for it. After that, we do PTR equal address of var. This will retrieve the address of var and assign it to PTR. The second option is to allocate room in memory for new things to point to. This will be discussed in next lecture. We already talked about struct a lot in this lecture, but another thing is that for a struct, it cannot contain an instance of itself as an element, but it can point to one. This is very useful because in C, there is no class. By using struct, we can group a bunch of variables together and use it as if we're using a class. By having this pointer inside the struct, we can easily make a tree structure or a linked list. Here on the bottom left, I'm declaring 3 struct variables. The first one is pt1, the second one is pt2, and the third one is a pointer to a struct. So we haven't actually really talked about how to access the element of struct. What we normally use is dot notation. For example, if you want to access x from pt1, you can just do pt1.x. Because, as I said before, pointer to a struct is very useful, so we introduce another notation, arrow notation. That one is specifically used for pointer, struct pointer. For example, to access the element x from ptaddr, you can just do ptaddr arrow x, and that is equivalent to dereference ptaddr then dot x. To copy a struct, you can do pt1 equal pt2. What it does is that it will copy all the contents from one struct to another. For example, if pt2 has int x equal 1 and int y equal 2, and p will point to pt2 itself, so p equal address of pt2. After you do this expression, pt1 equal pt2, int x for pt1 will also be 1, int y for pt1 will also be 2, p for pt1 will also be the address of pt2. Pointers to pointers. We can already talk about this a little bit in last lecture as C functions pass by value. So we have an array A, which contains 3 elements, 50, 60, 70, and an integer pointer Q, which points to the beginning of A. Then we call increment ptr Q. So what this function really does is that it will create a local variable P that copies the content, the value of Q, which make P points to the beginning of the array as well. Then when we do P equal P plus 1, we're moving P to the next element, but Q remains the same. That's why when we do printf dereference Q, it will actually still be 50. But what if we want to change Q? What if we want to move Q to the next element? How can we do that? The answer is we can pass a pointer to a pointer into this function. For example, right now, we're passing address of Q into increment pointer function. Now H points to Q. By doing dereference H equal dereference H plus 1, we're directly modifying the value that Q contains, which will move Q from the first element of A to the next one. And in this case, the reference Q will be 60. This is another question for pointers to pointers or double pointer. I recommend you pause the video and work through this exercise on your own. Okay, let's see what's going on here. So we have this integer array x contains the value 2, 4, 6, 8, 10. Our integer pointer points to the beginning of x, and the double pointer pp, which points to p. Then we have dereference pp++. So pp points to p, dereference p++ means we're modifying the value that p contains. That will become 44 because integer is 4 bytes. And we're moving p to the next element. So now p points to 4. Then we have dereference pp++. So dereference pp is p, dereference p is 4. We're incrementing 4 to 5. And that's the answer.